So now we're going to look at some of the techniques that you can, and processes you can perform using the Orfeo toolbox within QGIS. All right, so this is the image we've been using in some of the other videos. It's a Sentinel-2 image of the area around Prague. So what I've done is just composited the 10-meter band, so the red, green, blue, and near-infrared bands. All right, so first off, I'm going to talk about doing band decorrelation. So if we go into the, I believe it's, feature extraction, I believe. Nope. Image filtering. There we go. So under image filtering, we have this dimensionality reduction tool. So I'm going to open that. And then your input will be an image. You can define whether you want to rescale the output, so that is just rescales, I think, such that min and max fills the full radiometric range. We'll just leave it to no. Then there are some algorithms available for doing decorrelation. What we're going to look at is PCA, which is principal component analysis. So the idea here is to take the raw image bands and from those produce new bands which are not correlated with each other. So you're basically trying to take all the raw bands and generate new bands that capture all the variability in the data and potentially a smaller number of data points, or in this case bands. So the idea here is basically that variability is information. So you're trying to capture that by decorrelating the data. Okay, so anyway, we'll use PCA. The number of components is effectively the number of bands you want to get back. That can be from 1 up to the number of input bands. So what we have in this data set is 4 bands, so I'm just going to have it spit back 3. And then you can have it center and reduce the data if you want. You can set a background value. I'm not going to worry about that. And then you can see a couple of different outputs here. So we can get an output image file, so that's going to be your PCA bands as a multi-band image. You can get the inverse output image. I believe what that is how you could calculate the raw bands back from the PCA bands effectively. And then we can get the eigenvalues as a text file and the transformation matrix as a text file. So what I'm going to do is name these so they actually end up somewhere so we can look at them. Okay, so I'm going to go into my C drive here and teaching and QGIS demos. I'm going to create a new folder and we're going to call this PCA out. And then we'll name it, so we'll call this Prague PCA.tiff. And then we'll also name this inverse file. So we'll call this inverse.tiff. And then our two tables. So we'll just, what's the first one? Here is the, let's call it eigen.text. And then lastly, we'll get the transformation matrix. So we'll call it CM for TM for transformation matrix. And then we'll give again a .text. Okay, that should be everything. So now we're going to run this tool and let it spit back, hopefully, our transform data. Note again, this is raster processing, so depending on the size of the file, the number of bands, the extent, the cell size, some of these processes could take a while, potentially hours. But generally here we're going to use smaller data sets, so it's not going to take hopefully just a minute or two to process the input. Okay, so that's done. That wasn't too bad. So you can see a bunch of text that got spit out here. It's telling you the RAM limit for the software, the GDAL maximum cache size. Again, it's using some of these other toolkits, so like GDAL. It says it can use up to 8 threads. I have a processor with 8 threads. And then the processing block, so it works through the data in tiles or blocks, and then when it's done, it lists all of your output there. Okay, so let's hit close, and you can see that a new image got spit back here. So this is kind of interesting. Again, it's not really spectral bands now, it's decorrelated bands or principal components. And then it's being displayed here as like a 3-band image. And it does seem like it does capture a lot of the information, right? So we see clear differences between these fields based on like the amount of vegetation that's present. It does a good job differentiating like developed areas versus agriculture and whatnot. So again, there was probably a decent amount of information there to use. Okay, and then before we leave this, let's go into the folder where we save this and have a look at the, let's see, PCA, the output text. So I'm going to open this matrix file here. We're going to open it in WordPad. Okay, so what are these values? So what these values are is what you need to times each band by in order to get back the principal component. So generally this is set up, so this is the principal component 1, 2, and 3. And then what you're looking at here is the values you want to multiply band 1, 2, 3, and 4 by to get that. So we take band 1, multiply by this, add it to band 2 multiplied by that, band 3 multiplied by that, band 4 multiplied by that, and you get back a number, and that's what ends up in the pixel. So this matrix effectively shows you how to take your raw data and transform it into the principal component bands. Okay, and then these are just the eigenvalues here. And I believe that has to do with the amount of variability captured in each band. Generally, the first couple bands are going to capture most of the information. Okay, so that's an example of doing dimensional reduction or principal component analysis using the Orfeo toolbox within QGIS.